Honors Math 2, Unit 9 review. In Unit 9, we took everything we learned about the unit circle and we started applying it to graphing the trig functions horizontally, where your inputs, your angles was your x-axis, and how high it went and how low it went was your y-axis. And so we learned basically how an amplitude and a period was done with sine and cosine, and how that affected secant and cosecant, which are the cousins to the original function. So I'm going to start off with number 34, and then we'll go from there. Number 34 says, find the amplitude and period of the following. What we learned way back in Unit 9 was that the A value and the B values determined your amplitudes and your period. The amplitude was determined by what was multiplying the trig function, otherwise known as the A. How high it goes, or how low it goes, was determined by the A value. If I think about the A value being 1/2, what that does is it makes your trig function go as high or as low as that A value. Your amplitude would be 1/2 in this problem because your A value is 1/2. Your period, on the other hand, there was a formula for it. It was the period. I'm going to put the formula right about here. Period is equal to 2 pi divided by B. The period is equal to 2 pi divided by B. Your B value is whatever is multiplying the x. And so if you look at this and you see x divided by 2, that means the B value is the same thing as 1/2 times x. The B value is 1/2. If you're trying to figure out what the period is, what you have to do is do 2 pi divided by 1/2. That's that complex fraction. 2 pi divided by 1/2 is the same thing as 2 pi times by 2/1, which means that your period, 2 pi times by 2/1, is going to be equal to 4 pi. Now I just want to highlight this is the answer to 34, but we might as well remind you how we graph these things. That means that your fourth quartile would be 4 pi. That means that your second quartile exactly in the middle would be half of that, 2 pi. And then that means your first quartile of the cosine would be pi. And then that would mean your third quartile, otherwise known as where the 0 is, would be 3 pi. And I say that because when I taught you how to graph these things, we talked about figure out what the y value is, the amplitude. If it's a positive amplitude for cosine, it starts at the extrema, midline, extrema, midline, extrema, and we learned how to graph based off of that. I say that because they're going to expect you to be able to name asymptotes, zeros, and so on. If we're talking about a cosine graph, the zeros occur where the cosine graph is touching the x-axis. It's where the y value is equal to 0. If I were to draw a quick sketch, the zeros in the first period are going to be here and here in the first period. You can't see that, I just realized. So I'm going to go right there. As a matter of fact, the zeros are going to occur every time it goes down the line. So let's talk about where that's going to be. The first thing we would have to know is what's the period going to be? What's that end of the period? Is going to be 2 pi divided by b. Period equals 2 pi divided by b. The b value is pi over 5. Now, instead of dividing by pi over 5, why don't we take that and multiply by the reciprocal instead? Which means that the period is going to be at 10 radians. Not 10 pi radians, just 10 radians. It's like 10 times 3. I'm sorry, that's not correct. It's 10 radians. Every 1 radian is, I can't remember how many degrees it is. All I know is that pi radians is 3.14 radians as a decimal. So off the top of my head, that's just 10 radians. And if I want to know where the zeros are, half of this is 5. And then half of that, I can write it as a fraction, or I can write it as a decimal, doesn't matter. So I already know that in the first period, where the zeros are going to occur are at 2.5 radians, at 7.5 radians, and then it just continues. If I think about how many zeros are there, where does the zeros occur in the function? If I think about this is at 12.5, and that it's going to occur every single time. It's just going to keep going up by the same amount. We could probably write that the zeros are going to be at 2.5, and how far apart are these? These are 5 units, or 5 radians apart. Every 5 plus 5 plus 5, n, where n is an integer. So I'm going to write a very interesting answer for some of you. My answer for this is it's at 2.5 radians plus 5n. Because I have zeros here, I'm going to point zeros in the first period here and here. But in the second period, they're here and here. And then in the third period and the fourth period, there's zeros for infinity. So because it didn't say anything about where do the zeros occur in the first period, it doesn't say that. It says where do the zeros occur. I have to think, where do all the zeros occur? They are 2.5, and then it goes up by 5 radians, and then up by another 5 radians, and up by another 5 radians, and so on. So because these are 5 units apart, what I'm going to do is I'm going to say it's at 2.5 radians plus 5n, because we may be 1 set away, or 2 sets away, or 3 sets, or I could even subtract a set and go in the negative direction. The zeros are going to be 5 radians apart from the 2.5, and so on. That's basically like half a period. Kind of a complex answer. I would believe I wouldn't ask anything like that on the final. I think I would ask where do the zeros occur in the first period. You would only have to know the first 2. But this is the complicated answer because I've taught the highest level, and so we go from there. Okay? All right. Going to number 37. Says we're supposed to sketch 2 periods. So the first thing I would do is I'd figure out what my amplitude is. My A value is a -1. So I'm going to put down on my y-axis 1 and -1. I'm going to figure out what my period is. This is a secant graph. So I'm going to do the period is equal to 2 pi divided by b. B here is 2 pi. So my period is 1 radian. 1, 2, 3, 4 is 1 radian. The 4th quartile has to be 1 period long. 4th quartile, 1, 2, 3, 4. 4th quartile is 1 radian long. Half of that is 0.5. Half of that, 0.25. Half of that, or 3/4 of those, 0.75. We could do it as decimals, or we could do it as fractions. It doesn't matter. I'll put those in there as well. It says that we have to sketch 2 periods, so I will extend this, but before I do that, remember, secant is based off of 1 divided by cosine. So if I know what cosine's graph looks like, I can figure out what the secant graph would look like. The cosine graph is starting at the extrema, not the positive extrema, the negative extrema. And so what it would look like, I'm going to make this dotted. That's an upside down cosine graph. Extrema, starting in the negative extrema, because of that negative. Midline, extrema, midline, extrema. Now, if that's what we're dividing by, thank you. If that's what we're dividing by, then what we would get, if I have negative values being divided by 1 divided by those negative values, we're going to have something that starts here, and these are where the asymptotes would be. It has to approach the asymptote without actually crossing or get closer to it. Here's another asymptote where you would divide by 0. Division by 0 doesn't exist. So at 1 and above, we go this way. Below 1, at -1, we go towards the asymptote, and that would be 1 period. Well, it says sketch 2 periods. 1, 2, 3, 4. Let's continue this graph. Here's my second period. Here's another asymptote. Here's another asymptote. I'm going to finish creating what this graph would look like for 2 periods. That's a lot to remember. Comes back to you though once you do it a lot. If you need more notes, take a look at the Unit 9 notes. Let's look at 38. Now the first thing that I notice is that the highest it goes is 7 and the lowest it goes is -7. That tells me that the A value has to be 7. The second thing that I notice is that if I were to continue this thing down, let's just follow this path. We're going midline, extrema, midline, extrema, midline. That tells me that it's a sine graph because it starts in the middle.
Wouldn't the A value be -7?
Yes. No. The A value would be -7. The amplitude, I'm sorry, the amplitude is 7 because it's always the absolute value. Don't want to get you confused with that. I am going to talk about that in a second, but that's where I'm leading here. When you look at this, because it's a sine graph, because the sine graph is going in the negative direction first, that tells me that our A value should not be a +7. The A value should be a -7. The amplitude is always a positive value, but depending which direction things go in will determine whether your A is negative or positive. So now I know it's a sine graph. Now I know that the A value is -7. And then the only other thing I really have to think about is the period. And I know one period is 3 units long. If we went -3, the fourth quartile would be a +3. Well, what's the B value? If the period is 3, I can figure out what the B value is using the formula period is equal to 2 pi divided by B. I'm going to times by B. I'm going to divide by 3. And B would equal 2 pi divided by 3. Once you get that, you have everything you need to write the equation. You're using an x and a y axis. There has to be a y in your equation. Y equals -7 sine 2 pi over 3 x. It's a crazy answer, but the reason the answer is what it is because you're going down, you're going up 7 units, and we figured out what the period is to go -3. And remember, the reason I taught this to you this way is because we always did everything to the right. They're trying to trick you because they went to the left. And so things would be backwards if you just did everything on that side. But this is how I taught it to you, going from the y-axis to the right. So I'm going to do it everything off of that one and not the previous one. So now that we have that, and that's the review, that's the first half, is going over how to graph sine, cosine, secant, and cosecant. We didn't really graph a whole lot of tangent on that. But what we did after that is we started simplifying trig functions. And so what they're going to expect you to do is to simplify trig identities on 45 through 56. Before you do that, you may want to remember what your trig identities are, because the identities came down to three different kinds: quotient identities, reciprocal identities, and Pythagorean identities. If you do not remember those things, you want to go back to the notes. The ones that I'm going to write down at the top of my paper are the Pythagorean identities, because we're going to use those a lot. If you don't remember them, they are sine squared of theta plus cosine squared of theta. You all should remember is equal to what? Say it out loud. 1. I hope so. If we don't remember that, we're going to have some issues. But it will never look like that. Remember what I told you. Sometimes they'll have sine squared by itself, and they're going to replace it with 1 minus cosine squared. You have to manipulate these ones in your head to go from 2 terms down to 1 term. I'll show you some examples. That's the first one. The second one was, what happens if you divide everything by cosine squared? Tangent squared plus 1 is equal to, do you remember? Secant squared of theta. I think only 1 or 2 of you remember, so I'm glad I'm reviewing this with you. The third and final one is if you take the original and you divide by sine squared, you would get 1 plus cotangent squared is equal to, hey, a couple of you remember cosecant squared. And remember, squareds have to go with other squared terms. It doesn't work unless they are squared terms. So those are our 3 that we're going to use in these simplification problems. When I look at 48, 48 says sine of x minus cosine squared of x sine of x. These are those problems that simplify. How do we do it? You factor out a GCF. Pull out. This has a sine of x, so does that term. Pull out a sine of x. You get 1 minus cosine squared of x. This times this is that. This times this is that. And then 1 minus cosine squared of x is equal to something. If you subtract cosine squared of x over here, subtract it, then 1 minus cosine squared of x would be equal to sine squared of x, which now means we can replace this with that. And if you have a sine of x times sine squared of x, this means there's a sine of x times a sine of x times another sine of x means it's sine to the third of x. What I like about these problems are, if you know your trig identities, they simplify to something really small, nice and neat, compact, nice small package. It's really neat. Kind of fun. Some of you go, that's not fun. It is fun. You guys just got to see the beauty in it. There's a lot of beauty in that. I have 2 more, then we're going to be done. 49 is cosecant of alpha plus 1 times the cosecant of alpha minus 1. This is not squared. It's not squared. You can't use a trig identity unless it's squared. Well, then what can we do? We can FOIL. Cosecant squared of alpha, because there's 2 of them multiplying, minus cosecant of alpha plus cosecant of alpha minus 1. We FOIL it. And then a positive cosecant of alpha, subtracting a cosecant of alpha will cancel each other out, and you have cosecant squared of alpha minus 1. And so after I FOIL that out and I get to this, I go, oh, hey, that looks good. But if I have cosecant squared and I subtract 1, I can take it from 2 items down to 1 item. Cosecant squared minus 1 will equal something. What does it equal? Of alpha. Of alpha. And that's our final answer. Nice and smooth. We always give our answer. We never leave our answer as a complex fraction or a fraction. If we were here and we had 1 over tangent squared of alpha, you always move it up if you can at the end too. Lastly, those were simplified problems. We talked about how to prove things, and these were called one-sided proofs. How do we do a one-sided proof? You either turn the left side into the right side or the right side into the left. I'm going to always recommend take the more complicated side and turn it into the other side and don't touch the other side. So I'm going to leave this side alone. And then what I'm going to do is I'm going to use what it has, and I'm going to say, hey, I already have a secant. There is a secant. This is a secant squared, so I'm going to leave this one alone. I'm not going to touch that secant. It's in the numerator. It's the same thing as times cosecant of x over cotangent of x. Like I could, this times that is that over cotangent of x. And I'm leaving it alone. Why am I not touching it? Because I already have one. I just need to somehow turn this into a secant squared. Or not into secant squared, into a secant. So let's see. How can I do that? Secant of x times 1 over cosecant is 1 divided by sine of x using a reciprocal identity. Cotangent of x is cos, I'm going to use its quotient identity. Cosine of x divided by sine of x. I'm not going to touch this side. I'm leaving the right side alone. Now I'm leaving this secant of x alone, and I have 1 over sine of x, but instead of dividing by this, I'm going to times by the reciprocal. And what I notice is that those two sines of x's would reduce. And 1 over cosine is the same thing as secant of x. And what do you know? On this left-hand side, I'm getting secant of x times secant of x. My final answer, the left side is secant squared of x. The right-hand side is secant squared of x. You never stop until the left side is equal to the right side. And once you do, you have now proven that the left side is equal to the right side. I'm going to stop your notes right there.